You ever stop and wonder what really holds human progress back? It's usually not a lack of imagination. Nope. More often than not, it's just a lack of the right stuff. I mean, everything we've built, our cities, our phones, everything, is made from materials. And our ability to build the future, well, that's completely tied to how well we can understand and engineer the tiny little atoms that make up those materials. So if we want to understand our future, we've got to understand the stuff it's made of, right down to the atomic level. So let's dive in.
Okay, here's a perfect example. Think about this. The Wright brothers. They flew the very first propeller plane all the way back in 1903. But the first jet-powered planes, they didn't show up until World War II. That's almost 40 years later. And it's not because engineers didn't get the idea of jet propulsion. I mean, nature had already figured it out with things like the squid. No, the real problem, the thing that held everything up, was finding a material that could actually handle the insane heat. See, the problem was that early jet engines would get so incredibly hot, I mean blazing hot, that they would literally just melt themselves. Yeah, not great. So to solve this fiery, melty problem, scientists had to go back to the drawing board. But we're not talking about the engineering drawing board. We're talking about the atomic one. We need to zoom in way, way in to really get how they finally built a material that could take the heat and fly. And that journey, well, it starts with the atom. You know, for centuries, the atom was just an idea, a concept. It was something scientists were pretty sure existed, but nobody could actually see one. But unlocking its secrets, that was the absolute key to being able to design the world around us on purpose. The funny thing is, the word atom actually comes from the Greek atomos, which means indivisible. For the longest time, everyone thought it was the smallest possible piece of anything, like a tiny, unbreakable little ball. But then, as our tools got better, physicists realized, wait a minute, you can break it. The atom wasn't the end of the road at all. It was the doorway to a whole new world of even smaller, more fundamental parts. And what's so cool is how our picture of the atom didn't just appear overnight. It was built piece by piece like a puzzle. So first up, in 1897, you have J.J. Thomson, who finds this tiny, negatively charged particle, the electron. Then, fast forward to 1911, and Ernest Rutherford discovers this dense, positive core, the nucleus. He did it with that famous experiment firing particles at a super thin sheet of gold foil. And then finally, in 1932, James Chadwick comes along and finds the neutron, that missing neutral piece of the puzzle, right there in the nucleus. But wait a second. This discovery created a huge puzzle, right? If the nucleus is packed full of positively charged protons, and we all know that like charges are supposed to repel each other, then why doesn't the whole thing just fly apart? Well, the answer is a force so incredibly powerful it has a really simple name: the strong nuclear force. It only works over teeny tiny distances, but it's powerful enough to act like a cosmic superglue, holding that nucleus together against all odds. It's one of the absolute fundamental rules of our entire universe. Now, you have to remember, for decades, all of this was just theory. Nobody had ever actually seen an atom. That all changed in the 1980s with an incredible invention called the Scanning Tunneling Microscope, or STM. Now, this thing doesn't see with light. Instead, it runs this ridiculously sharp needle just over a surface, and it measures a tiny electrical current as electrons kind of tunnel across the gap. And the result? Whoa. We could finally create actual images of individual atoms. We could even start to pick them up and move them around, like the world's smallest Lego bricks. Okay, so we've found the parts of the atom. We've got our protons, neutrons, and electrons. But just knowing the pieces in a Lego set doesn't tell you how to build a spaceship, right? The next absolutely crucial step is figuring out the rules, understanding the forces that make these atoms stick together to form, well, everything else. It turns out atoms stick together mainly by sharing or trading their outermost electrons. And you can think of these connections, these chemical bonds, in two basic ways. Some bonds are like superglue. They're incredibly strong, almost permanent. Think of table salt. But other bonds, they're more like sticky notes, weaker, temporary. And you know what? As we're about to see, sometimes being a sticky note is way more useful than being superglue. And for the perfect example, look no further than our own DNA. It is an absolute masterpiece of material science. So the two long sides of that famous double helix ladder, they're held together by those strong, superglue-like bonds. That's what keeps our genetic code safe and stable. But what about the rungs connecting the two sides? Those are held together by the weak, sticky note bonds. And why is that? It's genius. It allows the DNA to easily unzip itself so it can be read and copied. It's strong where it needs to be permanent and weak where it needs to be flexible. Amazing, right? Now, these bonds and the amount of energy the atoms have, that's also what determines if something is a solid, a liquid, or a gas. So let's do a super quick tour. First up, gas. In a gas, the particles have way too much energy to settle down. They're just zooming around all over the place, bouncing off each other like a bunch of hyper-caffeinated billiard balls. Okay, now let's take some of that energy away. Let's cool things down a bit. Suddenly, the particles start to get a little friendlier. In a liquid, they're close enough to cohere, to stick together, but they can still flow and slosh around, kind of tumbling over one another, almost like a crowd of people moving through a room. And if we remove even more energy, well, they finally lock into fixed positions. Now, they're still vibrating a little. You can imagine them like a perfectly organized but kind of jittery army, but they can't leave their posts. And that, my friends, is a solid. And then there's the ultimate rule of matter, the big one, discovered by, you guessed it, Albert Einstein, E equals mc squared. We've all seen it, right? What it tells us is that mass itself is just a super concentrated form of energy. And because c, the speed of light, is such a ridiculously huge number and it gets squared in the equation, well, it means a tiny, tiny amount of mass can be converted into a truly mind-boggling amount of energy. That's the secret behind everything from nuclear power plants to nuclear weapons. Okay, so we've got our fundamental physics toolkit all laid out, right? We know about subatomic particles, we know about the bonds that hold them together. So let's circle all the way back to our original problem. How in the world do we build something that won't melt inside a scorching hot jet engine? Well, the answer lies in a technique that humans have actually been using for thousands of years, making alloys. An alloy is really just a fancy word for a mixture of metals. The classic example, of course, is bronze. You take copper and you take tin. On their own, they're both pretty soft metals, but mix them together, you get bronze, which is so much harder and stronger that it literally defined an entire age of human history. And just look at how cleverly our ancestors played with the states of matter to do this. Take this process, lost wax casting. First, they'd sculpt a perfect model of something out of solid wax. Then, they'd cover that model in clay, which would harden into a mold. Step 3, they heat the whole thing up. The wax melts into a liquid and just pours right out, leaving a perfect, empty mold. Then, they pour in molten liquid bronze. They let it cool down, solidify, and then they just break the clay mold off, revealing this perfect bronze statue. It's this beautiful dance between solid, liquid, and solid again. And that brings us right back to the solution for our jet engine. By mixing different kinds of atoms together in just the right recipe, we can create materials with properties that seem almost magical. For the jet engine, the answer was a whole new class of materials called, fittingly, superalloys. By blending elements like nickel and cobalt, engineers created a metal that could stay strong even in the absolute furnace-like temperatures inside an engine. And that discovery? It's not just some cool piece of science. It's the reason you and I can get on a plane and fly across the world in just a few hours. So, we solved the jet engine problem. Awesome. But you know how it is. With every huge leap forward, we start dreaming up the next one. So, what's the grand challenge for material scientists today? What's the next impossible project on the horizon? Well, how about this for an idea? A space elevator. We're talking about a tower, or maybe more like a super strong ribbon, stretching 62,000 miles from the surface of the Earth all the way up into space. An elevator car could just climb up it, taking people and satellites and whatever else to orbit without the fire, violence, and crazy expense of a rocket launch. Yeah, I know, it sounds like pure science fiction. And yet, just like the jet engine all those years ago, the space elevator isn't stuck because we lack imagination. We know the physics, we've done the math. The problem, once again, is a failure of materials. We simply do not have a substance that is strong enough, light enough, and cheap enough to actually build the thing. Our biggest, boldest ambitions are, once again, just waiting for us to invent the right stuff. So I'll leave you with this. The superalloys that we engineered by understanding atoms that made modern jets possible, and in doing so, they shrank our entire world. So the question is, what new material, born from that exact same deep understanding of the atom, is going to be discovered next? And could that be the one that finally lets us build our tower to the stars?